do you people, can you record the meeting? I think this one cannot record the meetings. I don't. Can you record the meetings? Are you able to record the meetings? So it'll be anything not so. So we can, so when we solve systems of linear equation, basically here, I am going to look at two main methods. So we look at direct methods for solving systems of linear equations, and also look at iterative methods. But so to start off, we can say that to solve system or a system of linear equation or systems of linear equations, we use two main methods. Two main methods. So this thing, if you start casting, starts misbehaving. So we use two main methods. So one is what we call the direct methods, and then two is what we call the iterative methods. So the direct methods are those methods in which, if you remove the round of errors, then they give accurate solutions. While iterative methods, they are methods where we start with an initial guess, and then we improve that initial guess until we get the required solution to some degree of accuracy. And so when you look at direct methods, basically, since we see that these methods are sensitive to a round of errors, we should be careful enough to try to minimize the effect of round of errors, because most of them are very sensitive enough to round of errors. And so to start off, we want to start with looking at the direct methods. So when I mention here that systems of linear equations, I mean there is no product of variables. At least every degree of a variable is to order 1. So there are no product. For example, if x, y, there's no product of x and y, there's no product of x and x. That means square. That's what we mean by a system of linear equations. And so, in solving a system of linear equation, I will symbolize that as ax is equal to b. So when you have linear system of equations, there are those systems in which you can factor out the matrix of coefficients, and then you remain with the variables. So such that, so you have ax is equal to b, where b is the vector of constants, a is the matrix of coefficients, and x are the unknowns. So here x, so x is a vector of x1, x2, x3 until xn, and then a is an n by n matrix, so it's square. And then so b is also b1, b2 until bn, they are vectors, or it's a square matrix of order n. So that's a system of linear equations. So we say the direct methods of solving ax is equal to b are such that, or maybe are those methods which give the exact solution in a finite, this is the key thing, in a finite number of steps. In absence of round of errors. So these are some of the key statements here. So these methods, they give exact solutions. They are accurate such that they'll give you exact solution in a finite number of steps. However, they only do that in absence of round of errors. If you introduce round of errors, some of these methods may give you different solutions which are not even realistic. And so it means that you have to be careful in when you deal with these methods. And so these methods are, e.g., so what can somebody tell me what are examples of the direct methods of solving systems of linear equations? Which methods do you know the direct ones that have you dealt with, or that you have dealt with? Which direct methods have you dealt with that you know? Even from high school when you solve those simultaneous equations? Ni mimi sisikiki kama maiki zenu ndio hazifanyi kazi. Taking time. No, at least mnani-mute mic. When I teach, when I'm writing, the screen is behind, so siwezi ona watu. So if you guys keep quiet, naweza kuwa najiongelesha huku kando huku, na kumbe watu wamepotea. Unashangaa nimetembea 2 hours na kumbe sina mtu, niko peke yangu kwa meeting. So at least occasionally you unmute and then you say something. So which methods do you know that you used in high school, starting from primary, if you looked at them somewhere else?
I remember in high school we used the elimination method.
Elimination methods, yeah. So here we shall give it a good name and call it Gaussian elimination method. Any other method that you looked at?
Cramer's rule.
We have, yeah, you have Cramer's rule. Any other?
Substitution method.
Substitution. Which one can I relate with this substitution method? How can I relate to it? But so for now, let me substitution method. But how can I generalize this substitution method when you substitute this and this? Yeah. I see the method. Any other method? But this one you looked at, was it when you went to, was it Form 4? But even at maybe at and I think is a common one. Do you know this method? It just, you get a matrix, you find the inverse, and you multiply by the inverse, both sides. So that's the inverse method. You have the friend of this one, which is called the Gauss-Jordan elimination method. And then we have what? We have LU factorization. LU factorization just basically is dealing you whenever you have any square matrix can be decomposed into the product of lower triangular and upper triangular matrix. So that's the LU factorization. And so when you decompose into lower and upper triangular, then it makes it easier to find the or solve for those upper triangular matrices. If you have lower triangular matrix, it's very easy to solve, or upper triangular. You just start either by back substitution, that's what you said, the back substitution method, or you start with the forward substitution. You start from above going downwards or from downwards going up. They are very easy, the triangular matrices. And so for this course, I will look at this. The other methods, I think you looked at them somewhere, so maybe I don't consider them repeating them here. And then I look at this Gauss-Jordan, and I look at LU factorization. So we shall look at these methods on how they are used to solve systems of linear equations. And after, we look at them on how these methods can be used to find other things. Like, for example, the Gaussian elimination method is used to find the determinant of a matrix. Gauss-Jordan elimination method can be used to find the inverse of a matrix. LU factorization can be used to find the determinant, can also be used to find inverse of a matrix. So beyond these methods being used to solve systems of linear equations, we will also use them to find those other aspects. And so, if there are no questions, I want us to proceed and look at Gaussian elimination method. So this method, what it does basically is that you start with a system of linear equations, AX is equal to B, and then you reduce it into an upper triangular system, such a system containing an upper triangular matrix, UX is equal to B. And once you have this upper triangular matrix, then it's very easy to now solve back by substitution. And so we do this by first of all noting what is called an equivalent system. If you have systems of two equations, what are equivalent systems? So equivalent systems are those systems which have the same solution. If I give you, for example, the first solution, x1 plus x2 is equal to, for example, 10, and then 2x1 plus x2, I give you one system aside, and I give you another system aside. If those two systems have the same solution, then they are called equivalent systems. So having understood those equivalent systems, we also have to understand what are equivalent matrices. And two matrices are said to be equivalent if one can be obtained from the other one by doing several operations, either by interchanging the rows, by adding multiples of other rows, by substituting other rows with different numbers. That's what we call the equivalent systems, or the equivalent matrices. So you start with the matrix A, and then you find equivalent matrix, upper triangular matrix corresponding to A. And so once you get these upper triangular matrices, and noting that equivalent systems have the same solutions, then we find the solution of this upper triangular matrix. So that's basically the whole idea of Gaussian elimination method. And so I write it down. If I speak more than I write, then you can pick some of the things on what we say. But so let me start by defining what an equivalent system is. Because we say that we are using equivalent systems. So then we can say that two systems, say AX is equal to B, and by is equal to C are said to be equivalent if they have the same solution. So if you get two systems which you can form, and then they give you the same solution, then they are called what? They are called equivalent systems. Let me try to, can I get an example? Maybe 2x1 plus x2 is the same as, so if this is 1, 2, that is 4. And then x1 minus x2 is the same as -1. So I'm trying to find the solution of that one. That is 1, and then this is 2. Yeah, and then so this is what I'm calling system 1. And then if I also form another system, maybe say 5y1 minus y2 is the same as what? So this is 1, this is 2, that will be 3. And then negative y1 plus 3y2 is the same as, so if this is -1 and this is 2, that is 6, that will be 5. So this is system 2. And so we can say that 1 and 2 are equivalent, since 1 has solution x1 is equal to 1 and x2 is equal to 2, while 2 has the solution y1 is the same as also 1 and y2 is the same as 2. They have the same, so you can verify that those are the solutions. If I put here 2, I put here 1, that's 5 minus 2, that's 3. If I put here 1, I put here 2, that's 6 minus 1. I think those are the solutions. So basically, that's the point, that two systems are said to be equivalent if they contain the same solution. Otherwise, they are not equivalent. So can you hold on for a minute? I want to reply to this email. I think 1019. So having seen what equivalent system is, can we also define equivalent matrices? So what are equivalent matrices? And then, so we say that two matrices, say A and B are said to be equivalent. If one can be obtained from another one by a finite number of row operations. If one can be obtained from another one by a finite number of row operations. So those row operations are like you adding 2 rows, you can subtract 2 rows, you can add 1 row to a multiple of another row, and so on. So basically, so the aim here is you try to reduce your system from A, where B in our case will always be upper triangular. That's a Gaussian elimination method. You are reducing a matrix from the normal matrix to an upper triangular matrix. And the difference with this and the Gauss-Jordan is, with the Gauss-Jordan, you reduce the matrix to an identity matrix. And whatever remains on the other side becomes the solution of your system. So that one, if you want to do it, you have to proceed with this, then it's kind of cumbersome. So it's just very good, mostly used for finding the universal supermatrix. So what's the procedure of solving a system of equations by Gaussian elimination method? And then I can say here that, so to solve the system Ax is equal to B by Gaussian elimination method. Let me write it as GEM. When I write GEM, I mean the Gaussian elimination method. Comma, we reduce it into an equivalent system UX is equal to, say, for example, C, where U is an upper triangular matrix. And hence solve by back substitution. So what are the main highlights of this? That if you want to solve the system by Gaussian elimination, then you reduce it into an equivalent upper triangular system, or an equivalent system UX where U is an upper triangular matrix. And once you do that one, then you solve it by back substitution. So those are the main highlights. And so the task is to try to evaluate this, or to go through this procedure. How do we reduce a system of equation, or a matrix A into an upper triangle? We can do this procedure by reducing everything, including the variables, or we can just get rid of the variables X, and then you only reduce the system and reduce the larger system, where you form a matrix A with the matrix B. So to reduce the system, to reduce AX is equal to B into UX is equal to C, we simply reduce A into U and apply same operations on B to get C. So you just basically only pick out the matrix A and reduce the matrix A into an equivalent upper triangular matrix U. And once so any operation you perform on the matrix A, you perform on the matrix B, the vector B. Like that in the end, whatever you get will be U and then the corresponding C vector. So in simple, we simply write the larger matrix by augmenting A with B to obtain. So when you want to start, you simply write A, and I'm just putting here a line just to differentiate that, to know that one side is B. And so you write in this form, where this is called an augmented system or augmented matrix. You have matrix A and then you just add one column which corresponds to the B. And then you just put here the dash line in between, which is so that you keep in mind that whatever you have on the other side is the matrix B. So I want to describe this procedure on a simple system, just the system of 3 variables. I can even try on 2, but maybe on 3 variables. And so having tried on this, then we see the procedure, then we can apply procedure to an example of our choice. So start thinking of an example in your head, or either 2 by 2 matrix or 3 by 3 or 4 by 4 that we will use. And so so I just want to illustrate. So consider the system A11 X plus A12 Y plus A13 Z is equal to, say, for example, B1. And then A21 X plus A22 Y plus A23 Z is the same as B2. And then A31 X plus A32 Y plus A33 Z is the same as B3. So consider this system. And so in this system, I said the first procedure is you identify the matrix A and write an augmented matrix. So that's the step 1. Is write down an augmented matrix. And what's an augmented matrix? Is simply the matrix of coefficients written together with the vector of solutions. So it is A11, A12, A13. And then I have, this is B1, A21, A22, A23, and then this is B2, and then A31, A32, A33, and then this is B3. So this is what I'm calling an augmented matrix. And I told you this line, if you want, you just remove this line, but you just put it so that you recall what this is. So speaking of matrices, do you know what a row echelon matrix is? Have you ever heard of something called that one, row echelon form of a matrix? What is it? So in short, I think the original form of matrix, how can I put it? Is a matrix in which the first non-zero element of any row is to the left of the first non-zero element of any row below it. And if you have any other rows, and if you have any zero rows, then they go to the bottom. That's the original form. That if I consider any two rows, right? If I consider any two rows, for example, the first row and the second row, and if I have here the first non-zero element here, then if you go to below it, so the first non-zero, so it will be start the first non-zero element. If I go below it, the first non-zero element of this row cannot be on the same level and cannot be ahead of this. Should be at least one level after it. I think is to the first non-zero element of the row is to the left of the first non-zero element of the row below it. So that's the row echelon form. And basically what we are doing here, so if you know that one, we are just going through the same steps of reducing now this big matrix into a row echelon form. We get the upper triangular matrix. And so we do this, first of all, by identifying what we call the pivot. And so the pivot, so the first non-zero entry or the first non-zero entry of the pivot row or the pivot column is called the pivot element. So like in this case, this becomes our pivot element. And so we use pivot element to identify what we call the multipliers. And so the multipliers are what we use to reduce the row below them to zero. Right? And so here, I can record rows just to reduce. I normally label rows so that you don't confuse. And then I may just label this as this is row 1, this is row 2, this is row 3. And so we want to reduce this matrix into row echelon form. And so by reducing this into echelon form, what does it mean? It means that you have to make these two to be 0. I have to eliminate, basically I have to eliminate these guys here, such that any row below that one should go to 0. And we do that one by identifying what is called the multipliers. So the multiplier, say lambda to 1, that means the multiplier for the second row will be the same as this element of the second row, A21, and then divided by the pivot element, A11. That's the multiplier here. And then so each row will contain the multiplier, and it's just the value of that row divided by the pivot element. And then you negate it. So the idea is, if you take the multiplier and multiply by that row and add to the pivot row, or the row containing the pivot, then it will make that number to be 0. That's the idea. No, you don't. Yeah, no, you multiply the multiplier by the first element, the eliminating row, and then, so this technique, what it does, it avoids you by the row you want to eliminate by anything. You keep it. You don't multiply by anything. That technique helps very much in finding the determinant, such that in the determinant, what we will see later on in the determinant, anything you multiply by the row, you are eliminating. Multiply is the determinant. And so whenever you multiply any row by something, you have to keep track of all those things you are multiplying with. You know what they are happening. By using this concept of multipliers, you are avoiding multiplying any row you eliminate by any number. You only multiply by the row you are using to eliminate. Does that make sense? I said the concept of identifying the multipliers is you avoid the rows you are reducing, avoid multiplying them by anything. So here, my purpose is to make this matrix to be row echelon form or to reduce it. Idea is to make A21 to 0 and also make A31 to be 0, those two I've highlighted. So since I want to reduce row 2 and I want to reduce row 3, I avoid multiplying those rows by anything. I can only multiply the row I want to use to reduce that row 2, but I don't multiply the row I'm eliminating or reducing. In that, if I multiply any row, if I happen to reduce row 2 and I multiply it by any number, then that number will also extend to the determinant. So if you are using this idea to find the determinant. And so you have to keep track of all these things as you go along. And so to avoid keeping track of this, where you can make a mistake, is just trying to be cautious and avoid multiply the row you are eliminating by a number. Maybe if we do an example, it will make some sense. But so that's basically the idea. And so the multiplier for this row is just this means eliminating row 2 using row 1. And then multiplier for row 3, 1 will be the same as negative A31, whatever I want to eliminate, and then divided by the pivot element. Those are the two multipliers. And so we want to reduce this matrix. Basically, what happens? When I want to reduce this matrix, then row 1 remains unchanged. So I'll just have this as A11, I have this as A12, I have this as A13, and then I have this is what? B1. So new row 1 is just the same as what? Row 1. That's our new row 1 is the same as row 1. Nothing happened to row 1. But so I want to eliminate row 2 basically by using these multipliers. And so I can say that my new row 2 is the same as what? Is lambda 21 row 1 plus row 2. Do you know why? Just let me just write this aside. So just take only the first number. If I multiply this lambda by A11, what do you get? If I multiply lambda 21 by A11, what do I have?
Minus A21.
Yeah, I obtain minus A21. And now, what happens now if I add now to row 2? So I'm adding minus A21 plus A21. What do we get?
0.
0. So that was the idea, that this multiplier will help us obtain this is 0. And the same idea, I can say that row 3, new row 3 is the same as what? Multiplier multiplied by row 1 and then plus row 3. You just take multiplier, multiply by the element you are eliminating. And then you add to the element you want to eliminate. So when I do this, since I'm reducing row 2 and I've not multiplied it by anything, this one will never affect the determinant. Determinant will remain unchanged. We will see these things when we want to find the determinant later on using this. But so Let me just call this A22 prime, meaning the new A2 obtained just by following the same procedure. And then this is A23 prime. Then this is B1 prime, no, B2 prime. I'm just adding prime to mean the new one. Then if you follow the same procedure, this will be 0, this will be A23 prime, this will be A3 3 prime, and then this will be B3 prime. That now becomes our new system. So if you follow the definition of row echelon matrix, it says that the first non-zero element of any row is to the left of the first non-zero element of the row below it. So if I check row 1 and row 2, it satisfies that definition, that the first non-zero element of this is to the left of the first non-zero element of the second row. That one is satisfied. So row 1 and row 2, I'm happy, right? Now the question goes to, what happens between row 2 and row 3? Does it meet that definition of row echelon form of a matrix? Does it?
No.
No. Correct. And it's a capital no. And so we identify the new pivot element. So when I come to this becomes my new pivot. And I can now use this new pivot to reduce this other guy. Now I cannot even see where my tab is pointing. I can now use my new pivot now to make this part 0, such that we satisfy that definition of, again, the row echelon form. And then we follow the same procedure. I define my multiplier, now in this case, lambda 3, 2. That means I am eliminating row 3 using row 2. That's why I'm just putting this label so that it keeps track of the row you are using to eliminate which row. But you don't label them this way, no problem. You don't have to label them. So this will be the same as I said you take the element you want to eliminate, A23 prime, divided by the multiplier, A22 prime. That becomes the multiplier, and not divided by the pivot. So that will be the new multiplier. And so if you follow this procedure again, remember now when I do this, I have not done anything to row 1. So that one remains the same as row 1, A1, 3. Then this is B1, right? Now in this just remains as row 1. In these new things I've done, I've not done anything to row 2. So I can now say another row 2 new one is just the same as what? Row 2, because I've not now done anything to this row 2 here of the new matrix. But what have I done to the row 3? I can say now the row 3 new is the same as what? It's multiplier row 2 plus row 3. And then, so row 2 here is also remains the same. A22 prime, A23 prime, and then this is B2. This is 0. If you do this procedure, this will be 0. And then I have A33 prime prime. And then this is B3 prime prime. I'm just putting prime prime to mean that they are new. So the question is this a row, does it meet the definition of row echelon form? Can you compare any subsequent rows and see if they meet that definition?
Yes, to me it satisfies.
Yeah, it satisfies because if you check, it meets all the definitions. Because first of all, it checks if there are 0 rows, then it puts them to the bottom. There are no 0 rows. And then two, if you compare any two subsequent rows, then the first natural element of the row above is to the left of each one. Then so it meets. And if you do this, so I'm just giving you some of these things are extra, maybe. I don't know if you looked at these things, maybe. When you want to find the null space, the whatever column space of a matrix, did you look at this, those kind of things? If you want to find the linear independence of matrix vectors and so on, you reduce the matrix. And so this is the pivot column. Also, this is also they are called the pivot. So these are pivot elements. These are pivot elements. And so there is no zero pivot column. All of them are just non-zeros. No, there are no zero pivot elements. If you find zero pivot elements, then you have linear dependence. But so basically, in short, now ignoring this part, what type of matrix do we have on this other side? Which type of matrix is this?
It's an upper triangular matrix.
Yeah, it's an upper triangular matrix, so I can call it U. And then this vector, the variable, so I can now take back my x's, and then it's the same as these are B2 prime, the B3 prime, which I can just call it as what? As C. I'm just giving them another unknowns, but those are the values. So this was the idea. We start from AX is equal to B. This is just your AX is equal to 4. And then you apply these row operations until if you do this, you obtain the new system. UX is equal to C. And then now you solve for this UX, that becomes the solution. And I said, in solving for UX, we use back substitution. That means just start from below going upwards. Everything research will be simplified directly. For example, here, what does it mean now? It means A33 prime prime multiplied by X3 is the same as B3 double prime. This means that X3 is the same as B3 double prime divided by A33 prime prime. So basically, so you start from here, you get the solution. And once you have this solution, you can now, if you go, can you compare the second row? It is A2 2 prime X2 plus A23 X3 is the same as B2 prime. But remember now, you have X3. So you just plug it here. And then you can now say that A32 prime X2 is the same as what? B2 prime minus A23 and then X3. X3, I know it, I'm just keeping it, but so you know that you know it. And so the only unknown becomes what? A32 prime, and then this is what? A32 prime. So it means at every point, you end up solving one unknown at a time. And then once you get it, you substitute and obtain another known. That is A32 prime. And also now having 2 and having X3, then you can go back to the first equation, where now you have A11 X1 plus A12 X2 plus A13 X is the same as what? B1. But remember here, we know X2, we know X3. So the only unknown we have is what? Is X1. Where I can say that now my X1 is the same as B1 minus A12 X2 minus A13 X3 divided by what? By A11. And so this procedure that I've done here, from here downwards, this procedure is what I'm calling MC. Is what I'm calling the. Is this orange one? Is the orange one visible?
Yes.
So this is what I'm calling the back substitution. If you have this is an upper triangular matrix. If you have a lower triangular matrix, then you use forward substitution. You start from above coming downwards. You obtain x1, x2, and x3. If you use back, then you start from x3, x1, x1. So are you happy or you are sad? We have gone through basically it's like we have done an example, but just an example with unknown A1s just in terms of variables. So we can apply this procedure now to any system of equations and see how this one is applied. So let me just call this. This was example number 1. It was just example, but in terms of unknown, just to illustrate the process. And now example number 2. Can I get an example from you guys? Just give me any system of equations that you have looked at, and then we can look at that one. Yeah, any system, provided it's a linear system of equations. If you want 2 variables, if you want 3. Okay. Okay. So I don't see the back. Okay. Samuel, do you have a
Yes,
question?
excuse me. Yeah, I had a question in regards when we were doing the row operations. You did say
Uh-huh.
that the determinant will remain unchanged.
Yeah.
Yeah, now we've done matrices since high school and then a bit in campus. And
Mm-hmm.
from what I get, determinant represents in maybe if you look at the matrix in 2D or 3D space, it represents the area, but I'm not really I know how to get the determinant, we all do for various matrices,
Mm-hmm.
but what would you tell us the determinant represents, the determinant of a matrix? What does it actually tell us
Yeah.
about the matrix? Because all you know is just
Do I,
how to use it.
do I really know? But determinant, it tells us, it says many things depending on where you are applying the matrix. And so, as you have said, one way it represents an area. If you look at this in terms of the triangle, because in finding area of a triangle, you can formulate it in terms of a matrix, and then you find the determinant. So it represents area of a triangle. A determinant can also help you to determine if you have what we call the coplanar system or the equations of line. If planes are traveling, then they are moving in opposite directions. So you want to find if their planes will not cross, and basically they don't belong to the same plane. You can use the determinant. Determinant also can also tell you about this when you are finding the transformation. So it tells you about the scale factor of a transformation. Is it enlarging? Is it decreasing? It just basically like it describes an expansion of something. It's a quantity describing an expansion. So it has several meanings depending on where you are applying or where the matrix is applying. I don't know if it makes maybe some sense.
Yes, it does. And when you get a negative
Mhm.
determinant, what would you say it means?
It's just basically the same as it means the opposite. If you are, for example, if you are doing the transformation, right, and you get a negative determinant, it just means it flipped everything. If you are having maybe, for example, a triangle facing this side, then you are having just like, for example, an image. If you reflect yourself on the mirror, then everything has flipped. So it just tells you that if it was an expansion, then you expanded, for example, by magnitude, it's the same as the determinant, but in opposite direction because of the negative sign. Mhm.
Yes, thank you. Thank you.
And those are some of the key things about matrices, the determinant, because you will learn many things about matrices, LU factorization, you need matrix expansion, you need orthogonal vectors, and so on, everything about matrices. And then so the key things about matrices that we can associate with matrices are the determiner, and this thing we call eigenvalues and eigenvector. And if you look at some, in some sense, they are all related because the product of eigenvalues, they give you the determinant. So it can tell you many things about the matrices, and then it can tell you many things about these eigenvalues, can tell you many things about the, when you are solving this application to the real world, and maybe looking at the population. It tells you whether you will grow unbounded or you will be bounded when you grow, the population even grow. So they are just numbers which give us information about matrices. And just by looking at those numbers, then we can tell which type of matrix we have. And by knowing the type of matrix and area of application, it tells us information on what we are looking at. Any other question, or somebody wanted to give? If you have questions, you can ask. Otherwise, somebody can give us an example, and then we can look at examples. Yeah. Is equal to 8. -4. Is equal to 1. Is it 2? 1, 2, 2. It does 1, 2, 2 work? No, maybe it will not work. I wanted to guess the solution, but I guessed the wrong one. Now, we said what is the first step? Is that step 1, identify the matrix of coefficients, and then you augment this matrix with the solution B. And so the matrix of coefficient here I can identify is 2, 1, 2. I have 1, I have -3, I have 3, I have 4, I have 2, I have 1. So if you have problem extracting this, then you let us know. And then I augment this with the matrix of the vector of solution, so constants 1. This. That's okay. If you don't want to divide, then I can take even row 2 to row 1. I can shift row 2 and it becomes row 1. You see, when you perform these row operations, feel free to, you can swap rows. You can basically swap rows. And then by swapping row, you don't change any solution, you just get the same solution. But basically, you're getting a given system. However, when finding the determinant, you should be careful. Anytime you swap rows, then you are flipping the determinant of a matrix. So if the determinant, for example, is -2, and then you swap rows, then you get it will be a +2 because it will change by a negative sign. And that just tells you what the question that was asked about, for example, if I'm looking at the area. If I happen to swap any 2 rows, I am getting the same area of the triangle, but I'm getting a negative sign, meaning I have flipped my triangle. So it's now facing the opposite direction. Some of these negatives have to do with the direction of flow if you are playing outside of the boundary. We have just basically looked at it from the opposite side. If instead of having the mirror head in front of you, you have just put your mirror behind you. So just basically you have turned the mirror the other side, the other way around. That's basically what these determinants tell you, that you have maintained the same thing, but now you're looking at it from another dimension. And so why am I saying this? That for this system, because you know that the scale factors, you divide it by the pivot element. And so I know that if I make this to be 1 here, then I'm dividing by the pivot element, then it will be good. But if I do this, can I introduce partial? I will talk about partial pivoting later on. For now, we are just free to do whatever we want. So let me use this example to illustrate some kind of possible things we can do. We can interchange rows, we can swap rows, we can do whatever we want. And so I told you, you can track rows. I can call this row 1, this is row 2, and this is row 3. And just also to remark that I'm doing this systematically, one step at a time. However, you can do multiple steps at a go if you can. Also, you don't have to write down, for example, row 1, row 2, and row 3. It's not a must. People just have them so that you track whatever operation you made. If you have an error, you are able to know the error you made somewhere. So if you are comfortable doing this without having to write row 1, row 2, row 3, go ahead and do them. It's nothing. So I said just the first operation I'm doing is swapping, for example, row 2 and row 1. And so it means when I swap, I'll have my new matrix in such that my new row 1 will be the same as row 2. And my new row 2 will be the same as row 1. And row 3 I've just maintained. And so this will be 1 minus 3, and then 3, and then I have minus 4. And then I have 2, 1, 2, 8. And I have 4, 2, negative 1, negative 1, and 1. So this operation I did might not be necessary. I'm just trying to tell you that whatever operations you perform on your matrix, it's not unique. And so don't move 5 steps, and maybe you look at your neighbor and you see your neighbor has a different 3rd step, and then you think that yours is wrong. Now you want to copy your neighbor's. You will copy the neighbor's correct step at the wrong point, and then you mix with your steps, and then you mess up everything. So this row operation step is not unique. The upper triangular matrix you get is also not unique. It just depends on the operations you make. The only thing which is unique, if you have a unique solution, is your answers must be the same. Does that make sense? So here, our multiplier is no, our pivot element is 1, 1. I'm just cycling the pivot element so that now you know them. And having seen that pivot element, I now want to delete this, right? And so by removing this, I identify multipliers. 2, 1 is the same as negative 2. And 3, 1 is the same as minus 4. Is it okay if I write it that way?
Yes, it is.
Yeah, because I just took the number divided by the multiplier and then you negate. And that was the reason why I put this to be 1, because I didn't want to deal with the fractions and decimals. So I swapped this to be 1. But we'll see later on that if you have numbers and if you are dealing with the systems, for example, you are putting this into a system, so MATLAB, Python, your computer, your calculator, whichever. And then those systems, remember that they have inherent errors, that they only deal with the finite number of digits. And so they round off. If you give, for example, 2 divided by 4, that one is, or 4 divided by 2, just is maybe 0.5, it will keep it, because that's not a big one. But to have, for example, a very large decimal, 0.11 recurring, it truncates or round off the errors. And if you have this, we call the sensitive systems, ill-conditioned system, which misbehave by random off, then this pivoting, whatever you have done here, makes an error. And then basically what it does is that you need to put the largest element to be the pivot element. That one we call it pivoting. If you do it on rows only, you call it partial pivoting. If you apply with the rows and also columns, everywhere you look for the largest element, you call it full pivoting. And that's what is implemented in most of these systems, implemented in those ones. They do the pivoting such that you try to minimize this round of errors. If you have terminated decimals, as I said, don't care. They will not do anything. But if you have recurring decimals, a round of errors may misbehave, as we will see later on. But so, having said this, row 1 has not changed, right? That is 3, that's -4. So row 1 is kept as row 1. And then row 2, what is row 2 now? I say that now new row 2 is the same as what? Lambda 2 row 2 1. What's lambda? That's -2. Let me just put here directly as -2. It is -2 row 1 and then plus row 2. And then lambda, this row 3 is the same as what? -4 row 1 plus row 3. So tell me, what are these operations? Give me these values. Just
0,
by performing this on 0.
-1,
Are you sure?
-5.
This is -3. Yes?
-5,
Are you sure? And so you see that I've asked 2 people that are you sure. So it means in the exam you should be careful. And by the only way to know these things and to be sure about them is by doing a lot of practice, so much practice. Give me
7,
the correct answer. It's 7.
7,
And the next,
-6, so in -5.
-5. Oh, wait. Next, Christine. So you should be sure. You should be sure about these things. And then next is what? Can you give me the next numbers now? Next is that's -4. That's 12 plus 2. That's 14. And then I have what? Minus 12 minus 1. That's
Excuse me, sir.
-13. Yeah.
Yeah, could you kindly show me how the multiplier d31 how it's -4 there? I think I wrote maybe the wrong formula. Is it minus a31 over a11 or minus a31 over a21?
So here I am using this to eliminate these two, right? And so a31 will be, you look at this, number in row 3 or number in row 3 divided by number in row 1, and then you negate. What you have, maybe I don't know if I wrote the wrong thing somewhere. You are to that the second multiplier.
Okay, thanks.
Are these numbers correctly? I've just written them. I don't know if they're correct. Yes, that's 12. 12 plus 2, that's 14. Then that is minus 12 minus 1, that's minus 13. Then that is 16 plus 1, that is 17. Hopefully it's okay. Now again, if you want to avoid decimal again, then you swap row 2 and row 3. Or I can still, if I was doing this myself, maybe I could have finished. I tell you that you can skip many of these steps, then you combine them in several steps. But so here I'm just trying to go through each step such that you understand the concept. So this is minus 3 and then 3. This is minus 4. Nothing changes. I am swapping these two rows again so that I avoid the. No, I don't have to swap. So I need to identify what is the new multiplier lambda 32. And tell me what is lambda 32?
-2.
-2, correct. And so row 1 is maintained as row 1. Row 2 is maintained as row 2. But new row 3 is the same as what? -2, row 2, and then plus row 3. Mostly these signs confuse people. Because, for example, if I put here negative, then most people will forget to put a negative in front, and then they get another negative. But so when you want to try that, if you want multiply, it makes all these numbers to be 0. So also this, nothing changes, -4, and then 16. And then last one, I'll have a 0. I'll have a 0 if you did this correct one. And then next is what? Is -2, that is 8. 8 minus 13, that's -5, right? And then this -32 plus 17, that's -15. So just confirm that they are correct one. Now, once you have obtained this upper triangular system, and then you are happy, now you start by substitution. Start from the below one. It means -5z the same as -15. That means z is the same as what? 3. Then once you obtain that one, go to the next. 7y minus 4z is the same as 16. That means y is the same as 16 minus 12 over 7. No, not 16 minus 12. It's supposed to be 16 plus 12 for what? That's 12. 16 plus 12. That's 28. That gives us 4. And then lastly, x minus 3y plus 3z is the same as what? Is the same as -4. That means x is the same as -4. 3z 9 minus 9, and then plus 12. And then we get what? That's -1. So hopefully those are the we didn't make a mistake anyway. But so basically the other things are just you go slowly through each step. You have calculators. If you think you might make a mistake, just key in these things in your calculator, not the system. This procedure here down, like the simplification of this part. So what I think this part makes sense, right? Do they?
Yeah, just one concern. You did mention by switching rows, the determinant changes. So even after switching the rows, are we certain that the final solution will always be unique?
Yeah, it's always unique. Is by switching rows, right? What are you doing to your system? You are just moving this equation here and move this one here. Does it change anything?
It doesn't change anything.
Yeah, so switching rows is just rearranging the system, right?
Yes.
Yeah, but if you look at that in terms of the coordinates, maybe before the coordinates, if you look at the triangle, it's just like if you switch rows, it's just like you are rotating your triangle, or somewhere you are flipping it. And if you flip it, then you are changing the determinant. So the determinant changes the sign. However, the solution does not change. So assuming you get some kind of an upper triangular matrix, right? And you get here their numbers, here their numbers, and then in the last row you get zeros, even if they are 4 by 16. And then you get here a number and zero number. Let me call it star. What do you think the solution will be? Hmm? First, we will see later on that if you reduce your matrix and you get 0 rows, or you get one full 0 column, then such a system, if there are rows of some vectors, then we say that those vectors are linearly dependent, they depend on each other. So one is a scalar multiple of the other, at least one of them can be expressed as a scalar multiple of the others. And in such a case, if you have 0 rows, your system may have many solutions or may not have a solution at all. It means for you to have a solution, then you have to belong to the null space. So it means the vectors B outside, they don't belong to the null space of the matrix A. And if they don't belong to the null space of matrix A, then they cannot be a solution. They cannot be something of this to give you the other one if you're finding the independence. And so the first case, if you have determinant is 0, that means you get the last row to be 0. This to be 0. So if this number is non-zero, right? Then here, what does it mean? It means here no solution at all. This system does not have a solution. It means basically the vectors, the right hand side of this does not belong to the null space of this. You can check what a null space is. However, if you have your system such that you have many things after reducing, so these are just putting, it means here you can have anything. I'm just only focusing on the last row, right? Here you can have anything. The last row maybe you also have 0, 0, 0 everywhere, and you have here 0. Also, this system here has many solutions. And such solutions, if you have a 0 here, then, so not many solutions. First of all, the determinant is 0. You have a singular matrix. And so here, there are infinitely many solutions. Did you guys look at the eigenvectors? Did you look at some eigenvectors and eigenvectors?
It was very brief, but actually, to come to think of it, it wasn't covered in class. That's last year.
But basically, what I wanted to mention is, if you look at eigenvectors, we say them they are ratios. In fact, it means there is so any scalar multiple of that eigenvector is also an eigenvector. They are just solutions. And if you look at eigenvectors and if you reduce your system and solve them, you'll always get at least one or two be zeros everywhere. And so you have this linear dependence of this. That's why you are saying many solutions, because each scale of multiple, that one is also a solution. So there are so many solutions. But so you have to distinguish between these two cases. If somebody asks you, gives you a system, for example, AX is equal to B, and then they ask, does it have a solution? Then you check by first of all finding this determinant of A. But instead of finding, you can just do this. If determinant of A is non-zero, then your system has unique solution. So I just said here, if det A is not equal to 0, then you have unique solution. We only have one and one only solution. However, if det A is equal to 0, then no solution if this first case is satisfied. I don't know. Let me try to match these two. If you have this, that if the determinant of A is equal to 0, then there is no solution if you have this case. But however, if determinant of A is equal to 0, and then you have this, if det A is equal to 0, then you have many solutions. So you miss that uniqueness. So you have three different cases. You can have a unique solution. You may miss a solution at all, or you may have so many solutions. And so always be careful, just by reducing, and you look at the last row. If it's zeros everywhere, like this, many solutions. If not zeros, if this is zeros and this is not zero, there's no solution at all. Because there is no way you are summing up 0 plus 0 plus 0 plus 0 plus 0 something, and then you get a number. There's no way. But do you people even need to look at partial pivot? Is it necessary to you? Is partial pivoting necessary? I doubt if it is necessary. So I think for your class, I can skip the partial pivoting. Partial pivoting basically means, I just illustrate it, is what I told you, that because of the round of errors of this, then I think I'll just explain what partial pivoting, but I'll not illustrate it. I just give you an example. But partial pivoting basically means you want to reduce the round of errors, and errors propagate. And so always in a matrix, you try to make the large element become the pivot element. So like if I was using partial pivoting, then this could be my pivot. You make the largest element of that row, the pivot row, to be the pivot element. That's the partial pivoting. If you are talking about the full pivoting, then you scan through the whole matrix, not this part, this side, and look at the largest element in magnitude, and then make it the pivot element. That's now what we call the full pivoting, right? And so maybe I can just write only, I don't have to illustrate this, but so basically the pivoting, what it does is to reduce the round of errors. And so I can here an NAB to reduce. Did you guys say you have another class today?
Yes, we have a physical class.
What time?
From 10 a.m.
I'm gonna join late. Can you please make sure that you'll be joining exactly on the hour at 8, all of you have joined, and then we start. But so I need to give you 10 minutes, right? We go to another class to change over, or 15.
It takes a
15.
bit of time moving from the hostel, maybe 20.
Kanu nasomea kwa hostel. But so 20. So we have about 5-6 minutes to wind up. So to reduce the effect of round of errors, then apply Gaussian elimination method with pivoting. So pivoting can be partial or full. So that's what we call the pivoting. And so basically in pivoting, I told you that in the partial pivoting, you scan through the rows, the pivot row, and pick elements with the largest magnitude to be the pivot element. So I'm just writing the points. So in partial pivoting, scan through the pivot row and make the pivot element as the one with largest magnitude in that row. And then you swap. So for example, if I give you, I will not solve because everything remains the same Gaussian elimination method. So the only thing is that here you pivot, you change. So for example, if you have the system 1, 4, 1, let me just write the matrix only, not the system. So you can just solve the system. And then I have 1.6 and I have 27.1. I have 1 and this is 50. And then I'll have what? I'll have that's 1.6, that is 12, and this is 1. And then I'll have that is 6, that's -1. So whichever comes at the other side, we don't care what comes here. But so what partial pivoting says is that look at this row, for example, this is a pivot row, and then identify which element has the largest magnitude. Which one? Hmm? So this has the largest magnitude. And so once you identify that one, you make that one the pivot. So it means you swap the rows that becomes the pivot. And so you rearrange the system such that you have 27.1, 6 minus 1, and then 1.4, 1, 50, and then I have what? 1.6, 12, and 1. So basically that's what the partial pivoting does. So from here to here, I've applied partial pivoting. And then you can do the rest of the steps. And once you reduce these first rows and you obtain the second number here again, you apply pivoting again to the second part. Now ignoring the first row and don't look at the last 2 rows. You do that one, even if there are 10. At each step, you look at the pivoting of the remaining rows and you keep going until you reach the end. So the pivoting reduces round of errors. And now, full pivoting, what does it do? Full pivoting tells you that you scan through the whole matrix and identify element with the largest magnitude. And so once you identify that becomes your pivot. So if I apply field pivoting, this becomes the largest. And so the question is, how do I bring this guy here? Is by interchanging column 1 and column 3. And then I'll have what? I'll have, remember, even it can, let me just even ignore the first one. Let me just look at this. If I want to apply full pivoting to this, still the largest is 50. It means I have to bring this 50 here. And how do I bring it? I apply two operations. One, interchange row 2 and row 1, right? And then interchange column 3 and column 1, such that I'll have 50 minus 1 and 1. And then I'll have 1, 6, and 12. And then I'll have what? This is what? 1.4. I'll have 27.1. And then I'll have 1.6. So here, what I've done, I'm just writing here. I've applied full pivoting. I hope you're writing some of these things down, whatever I'm mentioning. That in full pivoting, you scan through the whole matrix and identify the largest element of the whole matrix becomes the pivot element. In partial pivoting, you only consider the pivot row. In each step, you keep on looking at the pivot row. So once you use 50 to produce, and then you remain with the 2x2 system here, and then you scan through this 2x2, whatever is remaining, after assuming this as 0. And then you have the largest, becomes again the pivot, and then you keep that one. That's the pivoting. And then you reduce. So I told you the aim of pivoting is to reduce the round of errors. So any question? But as I told you, this is just numerical implementation. If I did we say that we'll be having some 1 hour somewhere to do some implementation numerical implementation in software?
Yes, you did suggest that.
When did we suggest it? No, which day?
Tuesday. I think you agreed. We agreed on Tuesday.
Oh, Tuesday at 8. Yeah, I remember Tuesday at 8. Yeah. So we can get some time and then look at this. So the first assignment is, first of all, just make brief notes on pivoting and solve example of your choice. Even if you can just write it through what I've said, just basically I just want to see if you understand pivoting. Just mention what partial pivoting does, what full pivoting does, and then do an example. It is not even something for 1 page. Just provided you, even if you don't write, provided just write 1 sentence of pivoting and then you do an example. That's what I want to see that you understand. And then 2, create a program, create a program that reduces a matrix into a raw echelon form. So use a language of your choice. If you want to use MATLAB, if you want to use Python, if you want to use R, if you want to use C++, any of your choice. And then 3, extend your program in 2 such that you can solve the system AX is equal to B by Gaussian elimination method. And then 3, no 4, test the program on the example of your choice. Because once you make a program that solves the system, you write a function, you get a function in MATLAB, whichever you want to use, you want to test, does it work? Does it give me the answers? Just pick example you want that you know the answers. Pick any matrix that you know answers. Start by 2 by 2. And then you feed in it, you give it. And then you check, does it give me the answers that I also obtained by hand? So when you do programming, that's what you do. When you make a program, test the program on a simpler problem you know the answers. Just pick a simple one, even just 2 by 2. Even you say 2x plus y, if I put 1, 1, this gives me 3. And maybe x minus 2y, it gives me, is it -1 or something like that one? If they're 1, 1. And then you test on this. And then you see, does the program give me the answers I know? If they are 1, 1, yes, then it's working. And then you test it now on a different program. It might work, but then it's on a different one, but also no solutions. It works. Then test on a 3 by 3. If it works, then it can work for any. Then you can even give it 100 things. Let me just put some 4 comments. Make the program to give warnings. If 1, you have many solutions, and then or 2, no solution. So you make the program such that if you know solution, it will output no solution, or there exist many solutions of this program. So basically, you make the program and then you check these questions, what we mentioned here. If you obtain this case, then you tell it outputs, there's no solution. Your system does not have a solution. And then if you have this solution, your system has infinitely many solutions. And then you can even say, if you get this, guess A3 to be, for example, 1, and then guess the other one. So the whole of this will be assignment 1. Don't be in a hurry. I want you to learn some of these things on your own slowly. The cut will be out of 30. The assignments I'm making will carry 15 marks. All of these will carry 15 marks. And some of this will just be, I want you to learn how to implement this. Some of them will review them. If we meet in the next class, if somebody who has done it, then he can just explain to us. Basically explain to us the program you made, somebody of Python, somebody of C++, of MATLAB, and then we learn the programming and we move. So on. Okay, so.
Excuse me, sir.
For those, yeah.
Yeah, I have 3 questions. 1, what's your
First of all, let me say this.
Oh, sorry.
First of all, before you ask your question, the class is over, so people are free to leave. But if you have questions, you are free to ask, or if you want to listen to what somebody is asking, also you are free to remain behind. Okay, yeah.
Yeah, 1, what's your suggested class text, the textbook? And number 2, you realize in MATLAB there's high-level abstraction where the complexities of this row echelon, the Gaussian is kind of eliminated. So the code, you don't really code what the program is going to do, but you're just using functions which are already created. So is that the approach you want us to take, where we just call maybe a function row echelon and then Gaussian and then just four lines of code, or you want us to do it in the crude
I want you
method
to understand what's happening in the background. Like some of this, I don't call it simple, right? But some of these basic things like echelon form, you can basically, I want you to understand what's happening in the predefined function in MATLAB. Just you give your matrix, check the matrix. In this matrix, identify the number of rows, the number of columns, and then follow those steps of row echelon form reducing, and then it reduces by automatically, so that you are able to implement what MATLAB does. And then you
yes,
see does what you get is, so basically I want you to like make the crash program of what happens in MATLAB behind the in the black box that somebody created.
yes, thank you.
And
then the last
yeah,
one.
on the text, I will, in fact, your system, because mostly I normally use many things combined, and some of them I just try to teach them from nowhere, and then I just get examples, random examples. So I don't have specific ones, but they are recommended text. I just take and then I send to you. I send you the options were recommended by your department for this course. And if I can, I will try to also to get their soft copies, and then I send you the soft copy of the same textbooks. So I will try.
Yes, thank you. And the last question was, I wanted to know if you experienced the solar eclipse on Monday. I believe it was Monday.
It was raining the whole day, so yeah, it was raining. And I think it was not this part of Canada, in the West Canada. It was not this part, and if it was there, then it was cloudy the whole day since morning to evening, so we could not even experience it. But I was to be in a meeting with somebody in the US, but he canceled the meeting because there was solar eclipse on the end, so he wanted to go and see the solar eclipse.
Okay. Thank you.
Okay. So I will try. Here I can get some textbooks, soft copies. So I'll try I think I have a course outline somewhere. I will check it if I have the soft copy, and then I check the recommended textbooks, and I try to download them, and I send the soft copies. If I don't, I have some other textbooks on numerical, but some of them you might get one topic is there, and other topics are not there, and then I send you the topics. And then I also told you a class rep that I will be, so the notes I'm writing here, I didn't want to do it weekly, but I'll try to make the PDF. I can make the PDF, and then I send you the PDF of the notes I'm writing here. But notice that sometimes I am saying many things that I'm not writing down. So also, if possible, besides what I write down, also when I say something, if you feel it's important, then you can try to note some of the things I'm saying down. Does it make sense?
Yes, thank you very much.
Yeah. Any other question? So if no further questions, we meet next week. So for the Tuesday class, I'll be communicating with the class rep before, because that one we said it will just be there in case we need some cover. So that one, if I don't communicate to class rep by Monday, then just know that it's not there.
All right. Have a good night.
Okay, you too. Good day.